Can you hear me? Yes, I can certainly hear myself. Hello everyone, good afternoon, and thank you for coming along to this presentation. I'm here to talk about the evolution of lead-free oxygen sensors in industrial safety. So firstly, an introduction. My name is Will Parrett. I'm Global Sales and Marketing Lead for DD Scientific. I look after sales directly in the US, Canada, and APAC. And I also lead a team who look after sales in the rest of the world. I also look after marketing communications, product marketing, and I've been in gas detection now for about 10 years, both in the OEM and the sensor manufacturer environment. So a bit about DD Scientific. You can find us on stand 1337, just over there. So we're a UK-based manufacturer of electrochemical gas sensors. We're established 2011, and we make more than 4 million sensors per year, currently running at a rate of about 1 sensor every 2.14 seconds, so very high volume. And we supply instrument OEMs in over 60 countries. The manufacturers we work with are mostly in industrial safety, process industry, air quality, and medical. And as you'll see from our slides here and from my new polo shirt, we were recently acquired by Teledyne Technologies, so we've just become part of a much wider organization. So what am I here to talk about? So this is not a technical presentation. You'll see I'm a salesperson, not a technical guy, but equally, it's not a sales presentation, so don't be worried. Hopefully it'll be somewhere in the middle. So I'm going to focus on the evolution of O2 sensor usage, what we're seeing as one of the world's biggest manufacturers of O2 sensors, the direction of travel we're seeing in sensor selection by OEMs globally, and the drivers behind these changes and why we're seeing these changes. And also the impact on end users, but also those within the supply chain, such as distributors and indeed ourselves as a manufacturer. So a little bit about O2 sensors in industrial safety. You guys probably know O2 sensors, so sorry if I'm teaching you to suck eggs here. But they're one of the most frequently used sensors in the industry, probably only behind H2S, which is found in a lot of single gas sensors, so the volumes for H2S are significantly higher, but it's a very frequently used sensor. Key applications, confined space monitoring is probably the biggest. And oil and gas, petrochem, telecoms is a very, very large market now, and food and beverage, as well as many other industries. Typical measurement range in industrial safety is 0 to 30% O2, capturing both depletion and enrichment. So we're looking for lack of oxygen as well as too much oxygen, which can cause an explosive environment. And the most commonly used format in the industry is the 4 series, which is the most widely used sensor format. O2 sensors are found in single gas, 4 gas, and multi-gas units. And the most common in a 4 gas arrangement, so that's a CO sensor, an H2S sensor, an LEL sensor, and an oxygen sensor. That's the most common place you'll find an oxygen sensor in industrial safety. So a bit about technologies. So historically, electrochemical sensors have worked on a galvanic operating principle. I'm not going to play this now, but we've got a great video on our website, which goes into all the technical details of how these work. But essentially, you have an anode, typically of lead, a cathode, and an electrolyte solution. And when exposed to ambient gas, the sensor converts a chemical reaction of oxygen into measurable current. And this sensor has been the go-to for industrial safety since the late 70s, certainly the early 80s, and it is still very popular today. It's still the most commonly used type of sensor we have today. So the benefits of galvanic sensors. So self-powered operations, they generate their own current via the chemical reaction. So they're quite easy to integrate into an instrument. They're field proven, so they've been around for many years. They're well established. They offer predictable linear output, consistent temperature response. They're very, very reliable signal they provide. They're compact, so they lend themselves to the 4 series format, as well as smaller formats as well. And they're low cost. So they're relatively simple design. They don't have a lot of precious metal content in them, which is a challenge with some other sensor flavors at the moment. So they're relatively inexpensive to make, and they're widely available. You can get them from several manufacturers. So I promised it wasn't a sales presentation. You can buy them from others, not just us. So, but what we're seeing is we're seeing a movement away from galvanic sensors. This isn't new, but it is gathering pace. So the industry's been moving away from galvanic sensors for almost a decade. And in the 7 years since we launched our first lead-free oxygen sensor, an amperometric sensor, we've seen customers go from 100% buying galvanic sensors to now around 70%. So that 30+% of sensors that aren't galvanic are a different technology. So there is a move away from galvanic sensors. So what we're going to explore is what's driving this change and what alternative technology is available, as well as what the future of O2 monitoring looks like. So some challenges, firstly, that we have with galvanic sensors. So lifespan. So galvanic sensors, they rely on a sacrificial anode to function. That anode has a limited life. So typically, a galvanic sensor will have a 1, 2, or 3 year life, depending on the specification. It won't go beyond that because it will have consumed all of its consumable content. They can fail abruptly. So as they near the end of their life, they can lose the ability to detect O2 and they can fail without warning, which is obviously a problem in confined space applications and situations like that. Leakage risk. So not all manufacturers are alike, but some sensors, they can have issues with leakage over time. So that lead within the sensor will expand, it will create internal pressure, it will cause the sensor to leak, and it will leak electrolyte. Now, when that happens, it can cause corrosion on PCBs, and that can be sufficient to actually kill an instrument altogether. So if you get corrosion on your main PCB, the instrument is a write-off, as I'm sure many of you will have seen in the field. So manufacturing galvanic O2 sensors is a challenge. Those involved in the industry among us will appreciate they're difficult to perfect. They're potentially even harder to sustain. Once you have the right recipe, the right manufacturing process, you don't want to change anything. It's very difficult to keep consistency in those sensors. And if there is a problem, it can sometimes be latent. So a sensor can pass end-of-line test, the instrument will calibrate and zero okay, but you might get a problem occurring later in life, perhaps 6, 9, 12 months into life. You might get a problem such as a slow T90 or an irregular temperature response. So the other key driver, or the key driver behind the move away from galvanic sensors is ROS, or RoHS, as our friends in the US call it, which I'm sure you know about, but briefly, it's ROS. It was introduced in 2006, applies to the EU and harmonized regions such as the UK, and it's there to protect health. So it's there to reduce hazardous substances in electrical components, or instruments, sorry. So there are 10 materials on the list that are banned under ROS, and lead, which is the primary anode material used in galvanic sensors, is one of those, which presents a problem. So look at the implementation of ROS. I mentioned it was 2006 it came in. It actually still doesn't quite apply to us yet in the safety industry. So when it came into force, OEMs were faced with the loss of a key component because there was no viable alternative at the time. So an exemption was granted, a time-bound exemption for the safety industry, the medical industry, to carry on using lead sensors until a suitable alternative came along. Now, before the advent of ROS and in the time since, sensor manufacturers have been working hard to develop alternatives, alternative sensors which provide similar or equal performance at a price point which the industry can stand. And that work continues today. Now, in the time since, multiple further extensions have been granted, so the can has been kicked down the road on the final ban. So we keep getting more time as an industry, but that time is up next year. So the last exemption expires, and it's unlikely another will be granted. So that clock has almost finished ticking. So the impact of ROS on OEMs. So when the exemption finally expires, and manufacturers have to apply to ROS, they will not be able to sell instruments into the EU with lead-based sensors. They will be able to support instruments which were sold before the implementation, so they can keep supplying spares. So we're talking about a new instrument issue here. They won't be able to bypass legislation. And I have actually seen a manufacturer do this, where they would sell an instrument, a battery, and a sensor separately on the basis it's a kit of parts and therefore it's exempt from ROSH. You can't be doing that. So that will be outlawed also. And manufacturers had to respond. So typically, they have either modified existing instruments to accept a lead-free alternative, or more often, they've launched new products into the market designed for lead-free sensors. So we've had a while on this, right? 20 years. So there aren't many 20-year-old instruments out there. There are some. But typically, manufacturers who've been developing instruments have had this in mind, and therefore they've been designing new instruments for lead-free sensors. So what's the alternative to galvanic O2 sensors? So in 2014, the first amperometric lead-free O2 sensors became commonly available, launched by City Technology, now part of Honeywell. And this, for the first time, gave OEMs a ROSH-compliant alternative to galvanic sensors. The sensors were robust. They were environmentally robust. They were mechanically robust, so they were good for the rigors of portable applications. They were typically fast to respond, faster than galvanic sensors in some cases. And they had an eventual failure mode that wasn't going to kill your PCB. They're quite passive, much more like a toxic sensor. So when they fail, they don't burst, they don't leak, they don't damage the PCB, which was much better for instrument longevity. And they were free from consumable content. So the fact they didn't have a sacrificial anode meant that the life extended beyond 5 years. So a very different proposition, moving from 1, 2, 3-year sensor to a 5-year sensor. There were limitations also, and we should certainly discuss those. So there were limitations with the early lead-free amperometric O2 sensors. So they require a bias voltage. So that is a voltage to pass across them, unlike the galvanic sensor, which produces a current. Now, if that bias is removed, the sensor would take a long time to warm up. Could be hours. So you couldn't just put an amperometric sensor into a device and then turn it off. When you turn it back on again, there'd be a prolonged startup. So the industry had to work around this. So they would either power, if the instrument's powered off, they would either power that sensor, they'd maintain the bias, sometimes with a coin cell in the early days, more likely these days with some sort of trickle supply to the sensor. But that meant the instrument was never off. So if you do turn an instrument off with that type of configuration and you set it aside, you'll come back to it in due course and the battery will be completely dead. So that was something of a challenge. It was also a challenge for fixed. So commissioning, you'd have to install a sensor, you'd have to wait for it to stabilize before you could zero it. Same with maintenance. Power outages in fixed applications, you lose power, the instrument's going to take a long time to start up again. So that was a problem. They also show a response to pressure. So when you show an amperometric sensor pressure, you will get a response as if you were seeing gas, which is obviously a problem for pumped instruments, of which there are many in the portable field. They were more expensive as well. They were over double the price when they first came to market, which was obviously pretty off-putting for OEMs. And they weren't field-proven. So, you know, people using safety-critical devices want to know they're going to work. They're going to work when they need them. But this sensor technology, when it was launched, wasn't field-proven. However, none of these challenges were sufficiently severe to outweigh the benefits of long life. And Honeywell actually put their lead-free sensor into their biggest selling instrument, the Microclip X3, and it sold very, very well. And that was something of a game changer for the industry. It was the first time that people saw it could be done, and it could be done effectively. So long life had a big impact. So on distributors perhaps more than others. So a lot of distributors, if you go back 10 years, 5 years, perhaps even now, they'll sell an instrument for very little margin on the basis they'll get the spares business in the future. That's how their revenue model works. So you take away the need for spares, you take away their revenue model. And what would often happen is the O2 sensor might need changing every 2 years. A CO and H2S sensor, which could be perfectly good for 4 or 5, would also get changed. So you're changing 3 sensors for the sake of 1. And that's still very common. So for OEMs, some OEMs, 30 or 40% of their revenue was reliant upon spares. So again, you take away that spares business, you take away a big chunk of revenue. So long life sensors were a threat to that revenue. And for sensor manufacturers like ourselves, long life means less cumulative sensor sales. It means we're selling an O2 sensor every 5 years, not every 2 years. And maybe even we're selling the CO and the H2S sensor every 5 years and not every 2 years. So it's been a challenge throughout the industry. The winners are the end users. So the impact of long life sensors for end users is overwhelmingly positive. So it's reduced their OpEx, it's reduced maintenance costs, it's reduced the need for training and sensor swaps, and it's provided enhanced instrument performance. And the real winners in this, as well as the environment and our health off the back of Roche, are really the end users who are getting longer life, better instruments out of this. So an important point to make here on voice of the customer. So just recently I was speaking to an OEM, and this is an isolated incident, it's happened before. They're quite price sensitive. And the exact comment was, customers aren't willing to pay for lead-free. Now, if you speak to end users, long life is extremely important to them. They know the savings they can make. You know, if you consider the implications of getting a fleet of 10,000 instruments back mid-life for a service, you've got to cover those engineers in the meantime just to change the sensor. Long life is something that the end users will absolutely pay for. So what I would say is it's important in voice of the customer, if you're an OEM, that the voice of the customer is actually the customer and not an intermediary who's making a lot of money out of sensor spares. So modern advances. So if we reflect back upon some of those early limitations of amperometric sensors, so they're still biased. You still need a bias to operate an amperometric sensor, but things have moved on since 2014. The challenge of the slow startup has been overcome. So modern amperometric lead-free sensors will start up from 0 power in under 2 minutes. So when you want to turn your instrument off, it's off. It's truly off. And if you're talking about fixed instruments, you can commission, you can service, you can have a power outage. The sensor will be ready in under 2 minutes, which is a really big deal, a huge deal for the industry. They now show minimal response to pressure transients. So they don't respond in the way that early lead-free amperometric sensors do. It's about a 10 times reduction in the amount of response. And because they're so fast now, the response is very quick and very short, not long, not large and prolonged. So an instrument can ignore that, so you're reducing false alarms significantly. Price. So amperometric sensors are now comparable on price to galvanic sensors. They have a little bit of precious metal content, but not enough to price them out of the market. Some are cheaper. So our lead-free sensor is cheaper than quite a lot of other manufacturers' galvanic sensor, which makes it makes it much more feasible for OEMs and end users. Amperometric sensors weren't field proven, they now very much are. So they're mainstream now. So there are hundreds of thousands in the field in applications. And in the case of ourselves, we've got more than 1 million lead-free sensors in circulation. So for new instruments, I don't think there is any reason any longer to choose a galvanic sensor over an amperometric sensor. The benefits of long life far outweigh any benefits that there might be from a galvanic sensor. So how has the market adjusted? So OEMs. So as soon as one OEM offered a 5-year life on an instrument, the others had to follow. We now see customers' instrument specs written around this. They demand a 5-year life. If you haven't got a 5-year life, you could be off the bid. Premature failures have become a thing of the past, and OEMs enjoy less returns, reduced warranty costs, and that's good for reputation and user experience. Standardization of SKUs is something we're seeing more often. So there are a number of large global instrument OEMs who have just taken the decision to standardize on lead-free globally. So rather than selling lead-free into Europe and galvanic into the US, they're standardizing on lead-free. It reduces their SKUs, it reduces complexity, and costs are similar, and users around the world are then benefiting from that 5-year life. And a lot of OEMs have adapted their business models. They don't rely on spares so much anymore. They've overlaid different revenue streams, such as software as a service and subscription packages for data and for calibration and things like that. So the industry is adjusted. Distributors. So distributors have had to refocus on selling instruments based upon features and benefits rather than just price. They're no longer always selling an instrument on the basis they're getting spares revenue off it. They're selling the instrument because it's the best instrument for the application. And for manufacturers, well, we continue to invest to try and produce the best lead-free sensors, and they're continually evolving. We've recently released a new product which has really set a new bar in lead-free sensors, and we continue, and they will improve as time goes on. So what might be interesting to discuss is the rate of change. So I've talked about this change. I've spoken about EMEA. So this is the increase in lead-free sensor supplies or amperometric sensor supply as a percentage of total sensors or O2 sensors supplied in Europe. So you'll see it's a steady increase, and it's ramping up as we get closer to implementation of Roche, which is to be expected. So currently almost 35% of O2 sales in EMEA are lead-free amperometric. So this is reflective of older instruments being phased out, new instruments being launched, but those old instruments are still being spares supported. So even if the instruments are out there with a galvanic sensor, they're still being supported with galvanic sensors, which is acceptable under Roche, and that's going to continue for a number of years. A lot of European customers are building, or European OEMs are building for European customers. They're not exporting, so therefore they need to have lead-free solutions, perhaps more so than some other regions. And we anticipate further acceleration of this trend in the next 2 to 3 years. So as those instruments with galvanic sensors start being replaced by new instruments, this is only going to increase. So US and Canada, another interesting one to look at. Much, much smaller adoption, so around 7% at the moment, but increasing. Now, what I would say is, I don't believe this is reflective of wider adoption in the US. There are some large US OEMs who don't source from us, who have standardized globally on lead-free sensors. So I think if you were to take that number as a whole, perhaps looking at manufacturers who produce their own sensors, it would be much, much higher. So there is certainly a move towards it in the States. But also, that said, US company, the US as a market is huge for US manufacturers, their domestic market, and also there's an industry which is very reliant upon spares and service companies. And those companies aren't going to want to see long life sensors. So that pushback we saw in the UK and Europe is going to be tenfold in the US. There's a lot of revenue on the line in spares and service. So there will be that resistance. But that said, I think as end user expectations change, end users get used perhaps in other countries to a 5-year life, reduced maintenance costs, they'll start expecting that in other world areas. So we do anticipate a continued growth there. APAC perhaps similar really, slightly less. A slower uptake, but a steady growth, and again, an uptick as we move towards Roche implementation. Perhaps proportionate to the number of instruments sold in EMEA. It's a portion of what they make in APAC, so therefore it only affects a portion of the instruments they make. As export sales increase and end user expectations again change, we'll probably see further adoption. We expect this number to increase as well. Again, over the next 3 to 5 years, we expect that to turn up. I think this is perhaps the most interesting one. China. So China is a market that's very much driven by price. Amperometric sensors are typically more expensive than galvanic sensors, yet we're seeing huge adoption in China. So they're currently the largest percentage globally of lead-free sensors is going to China, which I think is probably surprising for quite a lot of people. And it's not reflective of Roche. For the most part, the sensors that are sold in China are for domestic applications, not for import into Europe. So it isn't Roche that's driving it. Chinese manufacturers are typically less established. They're much more agile. They're launching projects more quickly. And instruments tend to have less features. They tend to be lower cost. And therefore, the lifetime of that instrument is a massive differentiator in the market. So if you can sell an instrument that has a 5-year life versus a 3-year life, that's going to be attractive to your customers. So it's that lifetime, that 5-year life, 5-year plus life, that is driving mass adoption in China. The service industry is less established in China as well. Instruments tend to be less serviceable. More you buy it once and you throw it away at the end of use. So therefore, you don't have that pushback from the service industry. It's all end user and OEM led. And we anticipate amperometric sensors becoming the preferred choice in the next 18 months to 2 years. We expect to tip over that 50% mark. As you can see, it's a pretty strong trend there. So globally, looking at those 4 regions globally, you'll see China's the biggest adopter, EMEA slightly behind, but all regions are moving away from galvanic sensors. So what's the future of amperometric O2 sensors? So the future is definitely amperometric sensors. As we've seen, those graphs are hard to argue with. That's where the world is moving. And that is due to long life. Roche started this transition. The products that have come off the back of Roche are better. They last longer. They perform better. They're faster to respond. And that's driving adoption now. So the whole industry is moving towards a 5-year life cycle away from a 2-year life cycle. And we anticipate amperometric sensors outselling galvanic by 2029. So I think as we move towards Roche, as we see greater adoption, as more end users see the benefits, that's going to ramp up, and that's what we're anticipating at the moment. We also expect an upward trend, as I mentioned, in the US and Canada, as end user expectations change. And we foresee the service industry in the US and Canada is probably going to go through a similar change to that in the UK and Europe, moving away from that service-based model to one that's focused more perhaps on the instrument itself. So the latest available sensor technology, so if you look at modern amperometric sensors, they've moved on a lot. 2-minute startup, no need for continuous power, response and recovery of less than 2 seconds. So compared to some galvanic sensors, which could be 10 seconds or more, they're very, very fast to respond. Minimal response to pressure transients. Baseline offset is very stable, so they're very good at sub 5% levels of oxygen. And a 5-year life, as I say, which kind of trumps everything in our world. So future development. So there will be future performance improvements beyond those I've just mentioned. We continue to develop these sensors, as do others, and we're constantly getting improved materials, which are allowing us to push the boundaries further. So sensors, amperometric sensors will get better. Sensor lifetime will extend further, and high-performance sensors will be available in smaller formats. And this kind of models the trajectory of where the industry is going, or certainly for us, from the historic now 7 series format, still used in a lot of fixed applications, through to 4 series, half-height 4 series, and then the next generation, which is M-cell, which is very, very small. Amperometric sensors will be available for use outside of that lower range of oxygen. So we're going to be seeing them used for partial pressure sensors, for the full range, as well as for trace oxygen monitoring as well. And that will take them into other industries outside of the safety industry. Some other industries have taken a different route. Some of them have gone galvanic, some of them have gone paramagnetic, but again, the benefits of those are not outweighed by amperometric, so we will see it in other industries. So just some resources quickly. You can find out a lot more on our website. Those videos I mentioned are on our website. If you want to know more about Roche, we have a white paper available on the website, which gives you everything you need to know about Roche from start to finish. And we also have a very useful email bulletin that goes out every 2 to 3 weeks, where we update our customers on this sort of information. Got about 7,000 subscribers at the moment, which you can sign up to by clicking this link here. I'm quickly running out of time. I think I've got 40 seconds left. But does anyone have any questions? If you have any questions that might take longer before our next speaker, you're more than welcome to come and see me on stand 1337, and we can talk them through. But does anyone have any questions now for me? No? Okay. Excellent. Thank you very much, everyone. Thank you.